Welcome to the Electronic Security Networking Technician Webinar Training, section number 4. The Electronic Security Networking Technician Training and Certification is a training and certification process for physical security technicians and personnel, people who deal with CCTV systems, access control systems, alarm systems, and their application onto IP networks and with IP devices. This program is administered through the ETA, the Electronic Technicians Association, and for you to complete the ESNT training and certification, you must complete all 9 sections of the webinar training, of which this is number 4. You must attend a 1-day hands-on networking lab, and that's also where you would get your written certification test. You can check our website, www.slaytonsolutionsltd.com, for certification class and testing dates in your geographic area. My name's Dave Engebritsen, and I'll be your instructor today. I am ESNT certified, I'm fiber optic certified, I'm also Network Plus certified. I've been in the electronic security business for 33 years, and I run a company called Slayton Solutions. We provide vendor-independent networking and fiber optic training for the physical security industry. Today's topic, or this seminar's topic, is network devices. We're going to talk about hubs and switches and routers and what they do on the network and how they function and how we connect up to them. So to get started, every device that is on a local network must have a NIC, or network interface card. In the old days, the NIC was an actual physical card that you added to your computer. Nowadays, the NIC technology, which holds the MAC address and performs the Ethernet function, that NIC technology is built into the motherboard of your computer or the motherboard of your laptop or desk or netbook computer. It's also built into IP cameras and encoders and NVRs and DVRs. The NIC is built in nowadays. It's not a separate unit. A couple things here for you to note. One is that you can have multiple NICs attached to a single computer. So, for example, the security director might have 2 NICs on his computer, one that goes to the security network where the cameras are, and one that goes into the enterprise network. So we can plug multiple NICs in using USB ports and some other devices. The second issue I want to point out is that wireless devices, Wi-Fi devices, also have what's called a NIC, except it's a Wi-Fi NIC. And so your laptop computer, if it has Wi-Fi, they all do, and it has a plug-in RJ45 female socket, which most all do, then what you've got is you have 2 NICs in that particular device that can be turned on or off, and they carry the MAC addresses that allow communication over the local network. Now, when we went from the original type of structured cabling system, where we had one piece of copper going around the building and everything was hooked up to that one piece of copper, and we switched to the structured cabling system where we've got a jack on the wall, and that jack, the female socket, RJ45 socket, is home run. It's on its separate cable back to the telecom closet, back to the patch panel. We had to have a way to hook the devices together. The first way that was brought to market was what's called a hub. Now, hubs are very simple. When an Ethernet packet enters a hub, the hub simply retransmits it to everything that's hooked up to it. And if you think about it logically, you see that this would work as a technology. However, it does a couple things that are undesirable. First of all, it wastes bandwidth. It sends packets where they don't need to go. The second thing is they are a security problem, because the guy in the upper right-hand corner of the screen, he might be the boss. The guy in the lower right-hand side might be the warehouse guy. But if the warehouse guy is running packet sniffing software and you're plugged into a hub, then he can see every data packet that goes into the boss's computer. So you can see the limitations of the hub, and you also see why hubs have fallen out of favor. In fact, they basically don't make them very much anymore. Hubs are what we call a layer 1 device. They extend the collision domain, which is important. Data packets can collide in a hub, and you can think of a hub basically as a repeater. Now, soon enough, they realized the issues with hubs, and they developed technology called the Ethernet switch. Understand what the switch does. The switch connects devices on the local network. So a local network is going to have one or more switches. A switch is a layer 2 device. That's a buzzword because switches read MAC addresses. You can see on the next slide what happens when a data packet enters the switch. The switch functions like an access-controlled parking lot. When the data packet, let's start at the beginning. When the person at the upper right-hand side of the screen, that computer, when that person turns their computer on in the morning, their computer registers on the switch and says, I've got this MAC address, and I'm plugged into, say, hardware port number 3 on the switch. So now the switch knows that MAC address is on that hardware port, and the switch records that in a file called a filter table. So now when the data packet enters the switch reads the destination MAC address, and then it parks the packet temporarily. It looks at its address book, at its file, and says, who's got this MAC address? At its filter table. Who's got this MAC address? Oh, hardware port number 3 has it. I'll ship it out there. So then the switch retransmits the packet incomplete out only to where it is supposed to go. So switches are smart. Now, switches, again, are layer 2 devices. They work with MAC addresses. Switches break up our collision domain. They basically eliminate the collision issue. We've got a couple of different kinds of switches, unmanaged and managed. We'll talk about them in a second. One thing I do want to point out, and it's illustrated in the picture you see on the screen, we've got 16 ports basically in the center, and then we've got a couple of RJ45 ports on the right-hand side of the switch. These are typically going to be uplink ports. Now, what makes those ports a little different is that in the modern switch, those ports are normally gigabit Ethernet. So they can do 1,000 megabits per second. And those ports are used to connect from one switch to the next switch. So we might be 10/100 Ethernet on our standard ports and gigabit on our uplink ports, which allow connection from allow a bigger bandwidth or a larger pipe connection from one switch to the next. Now, we can talk about the unmanaged switch very simply. It's the kind of switch that most of us have in our homes and in some of our businesses. These are switches that have no programming. You can't tell them what to do. There are no options. They're pre-programmed to do what they do. You plug them in, you power them up, they do it. And unmanaged switches work just fine for IP cameras and IP devices, the kind of electronic security devices that we might install. You don't have to have a managed switch to put on an IP camera. I've got 8 cameras in my house. I've got 3 unmanaged switches. That works just fine. But that's what an unmanaged switch is. You can also think of it as an inexpensive switch. Now, the other kind of switch that we'll talk about is what's called a managed switch. Now, a managed switch is going to be a 19-inch rack mount Cisco or HP or Foundry network. There's a few manufacturers, Cisco being big number 1, who put together big switches, 48-port, 96-port switches. Now, a managed switch is just that. It can be managed. You can tell it what to do. It's going to have an internal IP address. It's going to be accessible through, Internet Explorer. You can call it up, username and password, and you get into the switch. There's also ones that you can plug in and you can telnet into. But either way, if you've got the username and password, you can get on the switch and you can tell it some things that you want it to do. Now, understand that there's a difference between a $7,000 switch and a $17,000 switch. We're going to talk about some of the common features of a managed switch that you would find in most of them, but understand that, again, some switches have more stuff than others do. One of the things that managed switches do is they provide what's called a quality of service function. Let's take an example where we've got Dave's accounting company. We've got 40 accountants, so we got 40 computers. They're all plugged into a 96-port Cisco switch. So I've got 40 computers. I got 40 jumpers to the patch panel plugged into 96 switches, or plugged into 40 switches. It's working fine. Now the boss says he wants to go to VoIP telephone. So we're going to have 40 telephones we're going to add to our network because the VoIP telephone is a network device. So now we're going to have 40 more cables come in. We're going to plug them into the 96 port switch. We got plenty of space for them. So in that 96 port switch, we've got 40 phones and we've got 40 PCs. Now, the files that are used by the accounting company are typically going to transmit in TCP protocol, where there's receipts, where there's call and response, where we have pretty much guaranteed that when you call up that file, you'll get the whole and complete file. On the other hand, our VoIP telephone calls are going to usually be in UDP, user datagram protocol, which has no receipts and is generally used for things that are more real time. Now, the network manager may prioritize this switch and set the quality of service to say, you know, Mr. Switch, if you get really busy, here's what I want you to do. I want you to dedicate 60% of your processing capability to the UDP packets and 40% to the TCP packets. Why might he or she do that? They might do that because they want to keep the phone quality, the quality of the phone calls high. So they want to push the UDP packets through as quickly as possible. If on the TCP side, where we're doing our file transfers and that kind of thing, if it takes an extra second or 3/4 of a second for a file to open, most people don't care. But if you had that 1/4 second to 1 second delay in your phone call, you would care. You'd complain about the quality of the phone service. This affects us in the physical security business because based on the the compression protocol that we use in our IP cameras and video encoders, they may transmit in either TCP or UDP. And so how the and if we're on the shared network and we're running through that switch, how the quality of service is set can affect the quality of the video that comes through. Now, another thing that's available with a managed switch is port security, where we can have a table of MAC addresses where we can say only this MAC address can be plugged into this particular port. So this gives us more security in case somebody gets into our telecom closet and starts unplugging and replugging stuff and trying to do things. We can also have automatic port shutdown features, where if there's a broadcast storm or if a device starts going nuts and starts broadcasting bad packets or what are called raw data packets through, maybe it shuts that port off automatically. So we've got a lot of controls that can be set in our managed switch. Now, one thing that's important to know is that Ethernet, as we know it, and if you have an IP camera, video encoder, access control panel, whatever it is, Ethernet is not a supervised communication protocol as we understand in the physical security business. We're in the alarm business, and we have end-of-line resistors, and we have polled devices, and we want to know that that smoke detector is connected even when it's not it's not an alarm right now. But with Ethernet devices, if somebody turns off a computer, the network doesn't care, and there's no notification sent out. But if we want to supervise devices on the network, and in many cases we do, we're going to typically use another protocol called ESNT, or Simple Network Management Protocol. And that's going to act just sort of like a digital communicator works with an alarm system. We can program our switch to say, let's say it's Dave's accounting company, and we've got a server that stores all of our stored information, our files. We want to know that that server is connected to the network. We want to know that it's working. So we program the ESNT in the switch to say, watch that server that's plugged into port number 5, hardware port 5. If it quits communicating, if it loses power, if there's a problem, I want you to send me an alarm message. That alarm message is sent to the IT person's computer, and that alarm, based on the sophistication of their ESNT monitoring software, that alarm can generate an instant message or an email, or it can light a light or buzz a buzzer to enunciate that there's an alarm condition, that there's some important device has been disconnected or has died on the network. Now, another thing we're going to talk about here in just a second is the virtual LAN or VLAN. That's what's coming up next. And we've also got spanning tree and rapid spanning tree functions. Now, our managed switches can be layer 2. They also can be layer 2/3. And we'll talk about that when we talk about the VLAN. Now, our VLAN is important to us because if we're on the shared network and we're hooking our cameras, our encoders, our access control panels up to a shared switch, well, we've got a security issue there because inside people could potentially try to get onto our devices. But what the VLAN does is gives us a logical separation in the network. You can program a switch and say, these 4 ports belong to VLAN number 1, these 8 ports belong to VLAN number 2. And if you program it that way, the devices from VLAN 1 cannot communicate to the devices on VLAN 2 unless they're connected via a router, which connects 2 networks together, or it is a layer 2/3 switch, which combines some router functions with the switch functions. And we'll talk about this kind of as we get into it. But the VLAN is the modern way to subnet a network. One of the things that IT people want to do is maximize the number of switch ports that they use. It would be a simple process. If you want to have 2 networks, buy another switch, park it on top of the other switch, plug whatever you want into that top switch, plug whatever you want in the bottom switch. You got 2 networks, right? But those switches are expensive. It would be a lower cost if we could plug everything into one switch, assuming enough ports are available. But we still want to have that security separation. That's where the VLAN comes in. And we can select the hardware ports that are going to be on VLAN 1, VLAN 2, VLAN 3, VLAN 4, VLAN 5. And we can set them out. And normally, and this is an important thing to remember, the user's computers are assigned by their MAC address to go from one as to the VLAN that they are supposed to be on. Now, here's a drawing that shows you how, with a couple of different colors, how a VLAN can be laid out. Remember that a VLAN is a logical separation. It's in the software. We set it up and we say these devices are on this VLAN, these devices are on that VLAN. When data packets are sent from switch to switch, they are labeled that this packet goes to VLAN 2 and this packet goes to VLAN 3. This allows us to spread the VLAN across multiple switches. This is only doable if the switches are compatible with each other. If the customer has all Cisco switches, they are all compatible to the same level of VLAN, now we can spread the VLAN from switch to switch. We don't have to concentrate them all into one physical box. So this enhances our security and reduces our network administration. This also contains our broadcast and multicast traffic, which increases our performance because we reduce the number of devices that get hit with a broadcast packet when it goes out. Now here in this drawing you see where we've got 2 switches, and we've got, in some vendors, they talk about the VLANs in terms of colors, and they'll say there's a red VLAN and a blue VLAN, a green VLAN and a yellow VLAN. But here you see what can happen is if the switches are compatible, the blue VLAN and the red VLAN can spread from switch to switch. So if we have a situation where there is 3 telecom closets in the customer's location, and we want to hook 8 cameras up to telecom closet 1, and we want to hook 2 access control panels to telecom closet 2, and we want to hook the network attached storage and the viewer, the security director's computer, he's going to be on switch number 3 in telecom closet number 3. Well, we can, if the switches are all compatible, we can set up a VLAN that allows that security director to sit at his computer. He can see the cameras that are coming out of telecom closet number 1. He can access the access control panels in telecom closet number 2. He can access the stored video on the network attached storage in telecom closet number 3. It's seamless if the switches, and this is very important, if the switches are compatible and they can all do the same kind of VLAN. And what you're generally going to find at the enterprise level is the customer is going to have made a commitment and say, I buy HP switches or I buy Cisco switches. Pardon me. In which case, they generally will be compatible. But what's important to us as physical security people is this. If we are sharing the local network, we're going on the same switches as everything else, then what we're going to want to do is we're going to want to ask the IT person for a separate security VLAN for our cameras, for our access devices, our door locks, and everything else we're putting in. It adds an important layer of security. It keeps the local people who are not supposed to be trying to pick away at our devices or hack at our devices. It keeps them away from them because the VLAN's there. Here you see another example of a VLAN where we've got sales, human resources, and engineering spread across 3 floors of a building, but because the VLAN is set up, they can only talk to each other. We could draw another one of these ovals on the right-hand side, call it the physical security system, and have our cameras hooked up there. We can have as many VLANs as there are, ports on the switch, in the sense that we could have a VLAN where it's one device on one switch that can talk to one device on another switch. So a VLAN could be as few as 2 devices, could be at one separate VLAN if that was the desired result. So what happens with the VLAN, we kind of touched on this, is when packets are transmitted from switch to switch, they get what's called frame tagging, and this is also called the color or the VLAN ID, so that when a packet enters a switch, the switch knows which VLAN that packet is supposed to go to. Now, our VLAN setup administration can either be a static setup or a dynamic setup. In a static setup, the administrator sets up each port, says this is how you're going to perform. In a dynamic setup, the administrator takes the MAC addresses from the devices, and that it's the MAC address that assigns when the device is powered up, it's the MAC address of the device that assigns it to a specific VLAN. This is important to use when wireless is applied, when we have Wi-Fi and we have people carrying laptops around the business, around the office. And one day a guy might be sitting here, another day the guy might be sitting 100 yards away, but the MAC address on his Wi-Fi card is going to put him into the VLAN he or she is supposed to be in. Now, one of the ways that if a system gets really large, there is software called VMPS, or VLAN Management Policy Server software, that provides a database of VLAN connectivity. This is going to be used by IT people who have really large systems, and they have a large number of VLANs to operate and to manage and to monitor. Now, we've talked about our network switches. Remember, our switches connect everything that's in a local network, and we can have multiple switches. A switch can be connected to a switch. Now, if we want to go from that local network to the next network or the internet, we need what's called the router. Routers are separate and different from switches, although understand that if you have, for example, what I have in my house, a Linksys broadband router as it's called, it's a combined router and switch. The switch functions and the router functions are built into the same piece of plastic, the same plastic box. Now, our router is a programmable device, and our router is a layer 3 device. That's an important thing to remember from that TCP/IP protocol stack. The router is layer 3. It reads the IP addresses of the packets, and it's going to send them where they need to go. The router provides a very important function, safety and security function, for our local network. If you think about your local network like your house has a door on it. The door is to keep the bad guys out and keep the good guys in, right? Keep the kids in the house and keep the bad guys out. We got doors. Well, a router is an access controlled door. That's what it is. It allows certain people to come through, and it stops other traffic from coming through. Routers always have at least 2 IP addresses, one for the local network and one for the wide area network. Let's take a look at my router for a second here, and you'll see what I'm talking about. We go to my router here, and we can go to the status of the router. And you'll see here that when I click local network, it says that the IP address on the local side of my router is 192.168.1.1. That's also called the default gateway address, and it's one of our 4 magic keys. Remember, our 4 magic keys are the IP address, the subnet mask, the default gateway, and the port number. Some people call that, well, this router address on my local network, 192.168.1.1, is the default gateway address. Some people call it the IP address of last resort. It's the address that packets are going to go to if they can't find where they, when you type www.espn.com into Internet Explorer, espn.com isn't on your network. So the packets have to go somewhere to get out. They have to go to the door, just like I have to go to my front door if I want to walk out to the street. Well, the packets are going to go to the default gateway, which in this case is 192.168.1.1. Now, if we look at the router side, we're going to see a different address. This one has, under Internet, it has an IP address of 172.16.1.34. Now, what that means is this is actually the local address, this is the address on the public side of my DSL adapter, okay, because that's a Class B IP address. You see its default gateway is 172.16.1.1. So a router is going to have 2 IP addresses, one on the local network and one for the next network or for the Internet. Now, one of the security features that routers provide is a firewall function. It basically is going to be programmed or pre-programmed to stop unsolicited outside traffic from entering our network. We don't want every Tom, Dick, and Harry or hacker just cruising past our DSL adapter, cruising past our router, and getting into our network and rooting around. So when you type in http://www.espn.com, you're saying take me to espn.com, I want to look at the football scores. Well, when that feed comes back from espn.com, it's allowed back into the network. Why is it allowed into the network and to your computer? Why does your router allow it? The router allows it because it was invited. It was asked to come in. But now if somebody else tries to get through the router, generally the routers can be pre-programmed to stop that. The router also can give you some logging and report functions, and there's certain quality of service functions that the router can provide also. So here you see a typical network example where we've got a real simple network. We've got our PC hooked up to a network switch. We've got the local side of the router, 192.168.1.1, and we've got the wide area network side of the router, 67.32.12.16. So the router's got its 2 IP addresses. Now, one of the things that routers do is they basically ignore local traffic. If the computer in the lower right-hand side wanted to talk to the computer in the middle of the right-hand side, so it sends out its data packets, the router never even sees them. It doesn't care because the switch handles that. The switch handles it because, remember, the packets don't lead with their IP addresses in the local network. They lead with their MAC addresses. So the switch handles it the way we just talked about how switches work. Switch handles it, and the local traffic stays local. Now, when we are laying out our networks, there's a couple of different ways to do it. And there's some concepts that are pushed by some of the major vendors like Cisco, where they talk about 2- and 3-tier networks. Normally, we have a 2-tier network in our home or small business, and our 3-tier network where we have distribution and core switches. And I'm going to give you an example of that right now. Here's your typical 2-tier network, pretty much what you have at home, where you have your access layer and your backbone. Your network switch and your router may well be combined into the same box, and then your PCs, your IP cameras, whatever you've got hooked up to your network is hooked up to the network switch, and it's really pretty straightforward. Now, in a 3-tier network, what makes it different is the addition of, like some classifications of switches. We've got access switches. You see them along the bottom. Those are the switches that the remote devices are directly connected into. The PCs, the cameras, the servers and those network attached storage and things like that. Then we have distribution switches, which are connected to the access switches, and the distribution switches are then connected to core switches. Now, you might ask yourself, what's this all about? What it's about is redundancy. If you look at this situation closely and you look at how the devices, the switches are connected, like the access switches are both connected to, they're connected to both distribution switches. Each one is connected to both. Each distribution switch is connected to a core switch. Now, if we had a failure of an access switch, we would lose some of the devices. But if we had a failure of a distribution switch or a core switch, our network should still function. So by building a three-tier network, we're building in a redundancy level that can be very important at the enterprise level, because there's a lot of businesses that if their computer system is dead, they're dead. Their business is totally out of business. So that's why they build in these redundant layers of switches in the three-tiered network. So what they're aiming for is the proper amount of network availability. And generally this network availability, this performance is talked about in terms of mean time between failure. And where all network administrators and network devices and functions should be available more than 99% of the time. Sometimes you hear people talking about 5 nines of reliability, which would be 99.999% of the time. But I want you to remember one thing. A lot of manufacturers, particularly in the hard drive world, they will say, well, this hard drive, we brought out a new hard drive, and it has a mean time between failure of 4 years. Well, they just brought them out. How do they know it's going to fail in 4 years? And I want you to keep that in mind, because it's going to be very important when we are setting up the storage of video data or storage of security information, that we always keep in the front of our mind the fact that hard drives can and do fail. And when a hard drive fails, what are you going to do? How much data are you going to lose? And is your stuff backed up? That's important for you to remember, whether it's for your customers on their video systems or whether it's for your own, your snapshots of your kids at home. You got to back your stuff up. Now, there's a lot of talk in our industry about the bandwidth of networks, and I want to dispel the concept right here. Usually when you talk to an IT person and you say, well, we want to put these 20 cameras on your network, they're going to flinch, and they may flinch and say, well, it's going to take too much bandwidth. Well, how much bandwidth is there in a local network? There's plenty of bandwidth. If we have a good quality Cat5e cable going out to a camera, we do the connectors right, and the distances are correct, it's a 100 megabit connection minimum. And let's say the camera's putting out 10 megabits. It's a megabit camera. It's putting out 10 megabits per second. It's putting out 10 megabits per second. Well, can that go through the 100 megabit connection? Sure it can, right? Now, where the real bottleneck is in your network switches, or pardon me, where your real bottleneck is in the network is in what's called the throughput of the switch. But even a typical inexpensive unmanaged switch is going to have 2 to 3 gigabits per second of data throughput. Our managed switches are going to have much higher. They might have a Cisco switch might have 80 or 90 gigabits of throughput. So can that 10 megabits of video go through that 2 gigabit or 3 gigabits on an unmanaged switch? Sure it can. I've got megapixel cameras hooked up to $20 switches in my house. It worked just fine. So it's in the switches where there could potentially be a limit to the bandwidth, but there's plenty of bandwidth in those switches. The real problem isn't in the switches or the cabling. The real problem is in the internet connections, which are much, much smaller than the connections in the local network or in the managed or unmanaged switches. We need to provision our links properly, but that's more of an IT person concern. And we've got some other potential issues, such as denial of service and quality of service. These are things we're going to touch on a little bit later. Now let's talk about Wi-Fi and the components in Wi-Fi systems. Wi-Fi, you know, is Ethernet's wireless brother. It programs the same. It has MAC addresses and IP addresses. You can have a blended network like I have at home, where we've got some Wi-Fi laptops and we've got wired computers and we've got cameras and network attached storage and all kinds of good stuff can be hooked together seamlessly. Wired and wireless can be on the same network at the same time. Wi-Fi uses frequencies that are designated by the FCC as the ISM, or Industrial, Scientific, and Medical frequencies. This means that there's no site license required. If you want to add Wi-Fi to a network, it's a very simple process. You go to Best Buy or Radio Shack or wherever you want to go, buy yourself a Wi-Fi access point, or buy a combined Wi-Fi broadband router, hook it up in your house, and boom, you've got Wi-Fi like most of you probably have in your homes right now and your businesses. Now, understand that there are standards. They're set by the IEEE that set how Wi-Fi works, what channels it uses, what frequencies it uses, how it communicates, that kind of thing. So these devices are standardized, and generally, it wasn't this way a few years ago. But generally now all Wi-Fi devices will pretty much work together regardless of who the manufacturer is. Remember that our IP addressing with Wi-Fi is the same as our IP addressing with wired Ethernet devices. And this screen shows us the 802.11b and G, which are the most common Wi-Fi standards in use. What's coming on now is the 802.11a, which is 802.11n is in Nancy, which is has much bigger bandwidth, and I think we discussed that in an earlier portion of the webinar series. Remember that in Wi-Fi, the throughputs they talk about are wishful thinking. If they say that we're supposed to get 54 megabits on 802.11g, well, that's if you're real close to the Wi-Fi access point. The further away you get, the less bandwidth you get. Also remember that that is a shared bandwidth amongst all current users. If there's 10 PCs that are all using an 802.11g access point, they don't each get 54 megabits per second. They are sharing the 54 megabits per second. The other thing that's real important about Wi-Fi is that you must secure your Wi-Fi using strong encryption, and there's a couple other tricks that we'll talk about, but there's things you've got to do to your Wi-Fi to make sure that nobody else is using it. Because if they can access, remember that it goes right through your walls and windows, and a potential hacker can sit in the parking lot outside your building, and if you have unsecured Wi-Fi, they're behind your firewall and they can really create havoc. So you want to be careful about that. Now, one of the ways that we do set up our security is through how we program our Wi-Fi access point. And here you see on this screen where we have the System Service Set Identifier, or the SSID. The Service Set Identifier is the name of your Wi-Fi access point. When you go into a hotel like a Holiday Inn and you turn on your computer and the little box pops up that says wireless networks are available, and you click that box, and in the center a window pops open and it says, Holiday Inn, Fremont, and you click on that. Well, that Holiday Inn Fremont, that's the SSID name. That's the name of the access point. And for people who, like the Holiday Inn, who want you to use their Wi-Fi for free, they have their Wi-Fi SSID is broadcast out every second. It says, hey, we're here, hook up. Hey, come on, we'll talk to you. If you want to secure your Wi-Fi, one simple way to improve the security is to turn off your SSID broadcast. If you come to my house and you say, Dave, I want to use your Wi-Fi, I'd say, sure you can. Here's the SSID. You must type it in manually into your computer. So this is one way to secure your Wi-Fi from outside hacking. Now, there's all kinds of people, and I will confess that I've done this myself. When we have a house in Southwest Michigan that we do not have a phone line to, and the internet connection is very weak on my Sprint card, And we went driving through town one day because my wife had to get on the internet to do something, and the library was closed. So we went driving through town, and we found a Wi-Fi access point that was open, that was hooked up to the internet. And my wife was able to do what she did. This is or what she needed to do. And it wasn't anything illegal. She just had to get an email out. But this is an example of what's called war driving, where you just drive around with a laptop, and there's software that you can put in your laptop that's provided as part of this training program that you can scan, and you'll see all the Wi-Fi access points that your computer is seeing at that time. And it'll tell you if they're encrypted or not, and it'll give you other information. So we want to protect our Wi-Fi networks, and the key issue is to use strong passwords on our devices and strong authentication and strong encryption on our communications. If we encrypt our Wi-Fi, we've gone a long way towards securing our Wi-Fi communications. Nowadays, Wi-Fi connectivity is usually built into the laptops, it's built into netbook computers, and it's built into a lot of the Wi-Fi cameras that are coming out now from people like Axis, and Visonic has a Wi-Fi camera. Wi-Fi cameras are great. I love them because they are the simplest camera in the world to connect. All you do is bring the camera in, set it down, or mount it up on the wall, plug it in, plug in the power supply, program it, boom. It's on the network. You didn't have to wire it. Also, those cameras are movable. You can take them and put them in different places. When my daughter was very young, I would take her into her room for her nap. I'd put her in her crib. I'd take my Wi-Fi camera that had audio as well. I'd plug that in, aim it at the crib. I'd go back to my office. I'd open a window so I'm watching and listening to her while she's sleeping, while I'm doing my work. So you've got cameras that can move around. Nowadays, you're not going to see too much of what you see on the screen anymore, these plug-in cards. Most of the time the Wi-Fi is built into the devices. If we want to add Wi-Fi to an existing wired network, we need an access point. An access point wires in with Cat5e cable, and it requires power, either PoE power or a separate plug-in power supply, and it's got an antenna, and it gives us this Wi-Fi capability. Now, one of the things that you can do is you can use different style antennas to either increase coverage or limit coverage areas. Remember that a lot of times hackers will sit in the parking lot of buildings, and they'll try to hack into the Wi-Fi networks because the Wi-Fi is coming right through the window. Well, you can buy Wi-Fi antennas that are, say, 180-degree antennas and aim the coverage into your building. Or it's a 90-degree antenna and it's corner mounted, so that it just covers what you want to cover. If you don't want to cover the parking lot, don't cover it. Also, there's devices like this cantenna you see here that originally they made these out of Pringles cans that I've been told, I have not tried it, but I've been told that this can push a Wi-Fi signal up to a half a mile. So that's a consideration. If you want to increase distance, there's ways to do that too. Now, our Wi-Fi access point is often built into a box like you see here. This thing called a Wi-Fi router, it combines router functions, switch functions, firewall functions, and the Wi-Fi functions all into the same container. Now, there's two kinds of Wi-Fi networks we can have. There's the most common, which is the access point type. The other type that's illustrated in the lower right-hand side of the screen is what we call an ad hoc network. If you and I were sitting at a table and we wanted to share some files between our two netbooks or laptop computers that both have Wi-Fi, we could program our two computers to talk to each other. We don't need the access point. In fact, if you read my first book, there's a chapter in there that talks about how you can take a wireless surveillance camera and take a laptop, make the laptop a DVR, and now you've got an instant surveillance camera that could be installed, literally installed in minutes for, one of these situations where the customer needs surveillance right now. He needs to record it right now to, catch somebody stealing out of the stockroom or something like that. Now, another kind of wireless network that typically uses the Wi-Fi frequencies are these mesh networks. There's a couple of manufacturers of these, and I've talked to some dealers who've had pretty good success with them. What these do is provide you with either a point-to-point or a point-to-multi-point connection so that we can transmit our video, our access control information, whatever we want to do, and we can transmit it generally over pretty big distances up to a mile. Now, there's a couple things to consider here. One of them is this is going to be a line of sight issue. You are going to have to be able, if you're thinking I'm going to put this transmitter or this transceiver on this building, and I want it to transmit to that building over there, well, you've got to be able to see it like a rifle shot to make it work. And remember that trees get leaves, and leaves in the spring and summer are excellent attenuators of radio signals. So you can't shoot through the trees. You got to shoot over the trees to get the signal so that you truly have line of sight. But these systems can work very well in situations where you just can't get cable from point A to point B. Places like harbors, some college campuses, downtown areas. There's places where the fiber's not there, the cable's not there, there's no other way to do it. You can look at these devices. Now, they'll use the Wi-Fi frequencies, but some of them do not actually use the Wi-Fi protocol. They use a proprietary communication protocol. That might be a better idea, because remember, here you're pushing your security signals all through the air in the scenario you see on the screen, and potentially they could be intercepted, and potentially somebody could try to crack into them. And it's a lot easier if they're in one of the standard Wi-Fi protocols as opposed to being in a proprietary protocol. So this is one place where a proprietary protocol might be advantageous, is in something like one of these mesh networks. As I mentioned before, there's different kinds of antennas you can get. The basic antenna that comes with a Wi-Fi access point is an omnidirectional antenna. It goes in all directions, but we can get directional antennas that will either give us a wider, or should I say a less wide coverage. We can shape and tailor the coverage, the radio frequency coverage, to do what we want it to do in terms of gain and alignment. Now, we talked about it before, but we got to talk about it in some detail. We've got to back up our data. Hard drive failures are a real thing. So what are we going to do? We got to back it up somehow. We can back it up via separate disk drives. We can back it up with tape backup. We can burn things onto DVDs and CDs. What's ideal is a backup system that does it automatically. And you'll note here on the slide it also talks about system configuration backups. What happens if a switch fails or loses power? What happens to our network then? So we have to have disaster recovery strategies, particularly having to do with power failures. Because power failure, you need to think about your security system you're installing and say, if primary power fails at this building, how much of the security system are they going to lose? And how important is that? How many cameras will go down? If we're plugged into the UPS might hold the cameras up for 5 or 10 minutes. If we're doing PoE, power over Ethernet, but is that long enough? So this is one of the considerations we have to have. Now, in terms of network storage, there's a lot of different ways that we can store our video onto networks. Network storage for video is nothing more than a software set that records the video that you want to store onto a hard drive or onto a network attached storage, which is basically a hard drive, and then allows some kind of access with usernames and passwords so that people can view the recorded video. You can store it on your own desktop PC if the drives are big enough. You can have network attached storage. You can have an NVR, which is basically network attached storage, that's going to store the video and allow a user interface to it. But we've got to have a way to do it, and we may, in some cases, we may want to have a redundant storage over the internet so that our video data is backed up into the internet so that if something happens to that local machine or that local device, we've still got the video stored somewhere else. In fact, I have cameras in my house that are not only recorded at my house, but they're also recorded on the internet, so that if something were to happen to, the device in my house, I've still got the video on the internet. So there's ways to record things in multiple places if that's what we want to do. Now, our storage considerations are going to come down to the issues of bandwidth and resolution. We may want to look at products, they're going to be higher end products, that have dual streaming capability. A product that has dual streaming capability might send, maybe you're sending 5 frames a second to storage, but you're sending 15 frames a second to the live viewing screen. You give a good view for live viewing, and you're storing at a lower resolution or a lower frame rate so that you reduce your storage requirement. Now, if we have network connected storage, it can be both a video source and a destination, and it's most likely that if we have network connected storage, that's going to have to probably be on a gigabit Ethernet connection, so that if you have multiple cameras, particularly megapixel cameras, if we have multiple cameras coming in, there's a big enough pipe for them to travel in and a big enough pipe for them to come out if people want to view them. So these things are important issues when we're thinking about video storage. Now, thankfully, most of the major vendors like Axis and others have video storage calculating software that is easily available or is free, that you can figure out, if I put 20 cameras on this network and I want to store 10 frames per second at this resolution, how much storage bandwidth, how much storage space do I need if I want to save 2 weeks of it? And it's going to come up and calculate it, and it's going to tell you how much storage you will need. So now, when we get into a system that's going to give us an automatic redundant storage, we start talking about RAID configurations, or redundant array of independent disks. This is an automatic system that software and hardware put together so that we get our data is redundantly stored, so if something fails, we're still in business. The one kind of RAID that's quite common is called RAID 1, and it is simply disk mirroring. We've got at least 2 disks or 2 sets of disks, and everything that goes on disk 1 goes on disk 2. Nothing to it. And if disk 1 fails, you still got disk 2, and all your data is there. Now, this is what's called disk mirroring, and all the data is copied to both disks. Now, another configuration that's popular is called RAID 5. And with RAID 5, you need at least 3 disks or 3 sets of disks. And what happens here is the data gets striped across all 3 disks, and then there's a parity check that is put on one of the disks, so that in the event that any one disk fails, the data can be reconstructed through the parity check so that it can be reconstructed and brought back to what it was. Now, the reason people use RAID 5 is when you have a huge databases. I'm talking really big ones. When you have a huge database and you want to search it or scan it or whatever, if you're working a RAID 5 drive, it is faster to read across all 3 or 4 disks than it is to try to read it all out of one disk. So it speeds up access to data, which is why RAID 5 is a very popular configuration. But these are things to remember when you're thinking about how you're going to store the data. There's vendors like Nuo that make NVRs for our industry, and even their least expensive one, the one I got here in my house, has a RAID configuration that you can have 2 disks, and you can do disk mirroring, so if one disk fails, everything's on the other disk, so everything's good. Remember that you've got to back your data up, and an automatic backup system is the best way to go. Now, this is the end of Section 4 of the ESNT training, presented to you by Slayton Solutions. There are training and reference manuals that are available if you want to purchase them. There's the Technician's Guide to Networking Security Systems, and there's the Technician's Guide to Networking for Security Systems Enterprise Solutions. These are 2 books that I've written. that detail a lot more of the information that we're covering in this training program. You can purchase these books at ADI, or you can buy them at our website, www.slaytonsolutionsLTD.com. We also have the ESNT study guide, which may be where you got this webinar to begin with. But in there, there's PDFs of all the webinar sections, so you can print them out, the recorded webinars, and there's a quiz for each section of this webinar training series, a quiz with answers. And you should take that quiz to test your knowledge to make sure you're ready to move on to the next section. And you can secure your future in the physical security business with ESNT training and certification program. I thank you for watching this webinar, and we'll be moving on to Section 5.